Hello, this is Orenge Pelvis EDS 3754/23, and this group P. We are here to discuss questions, 5 questions on half-life problems.
My name is Mercy Kageni. My registration number is EDS/3680/23. I am going to be solving the question number 1, which asks for the relationship between half-life and the decay constant. Half-life is the time taken for a radioactive nuclei to decay, and the decay constant is the probability of nuclei to decay per unit time. So radioactivity is exponential. We have the number of the undecayed material after a left time t, which is equals to the number of atoms that are left after the decay. Since the radioactivity process is exponential, we have the number of undecayed nuclei, which is equals to the number of atoms left, then exponential minus lambda. Lambda is the decay constant. Then we have the time t. Half-life is represented by t half. So we are going to have this nt is equals to number of left atoms, e the exponential minus the decay constant time, then the half-life. So over here we are going to have number of undecayed constants, then the half-life, then the number of left atoms, divide by 2. Number of left atoms divide by 2, then we equate to number of left atoms, then exponential t negative lambda t 1/2. We are going to cancel the n naught, so we have a half equals to exponential negative lambda, then the half-life. To remove the exponent, we are going to introduce natural logarithm. So natural log of a half then equals to negative lambda, then the half-life. So natural log of a half is equals to natural log of 1 minus the natural log of 2. The natural log of 1 is 0, so we get negative natural log of 2. Now the negative natural log of 2, we're going to equate it to negative lambda t. My god, yeah, we remove the negative, so we have natural log of 2 is equals to the decay constant, then the half-life. This is the half-life. We make the half-life the subject of the formula, so we have the half-life is equals to natural log of 2 over lambda. This shows the relationship between the decay constant and the half-life. Passing on to question 2.
I'm Philip Ouma, registration number EDG 3645/22, and I'll be tackling question 2, which deals with the calculation of remaining fraction after 30 days. And for our case, we'll use phosphorus P32, which has a half-life of 14.3 days. So we first find the decay constant, which we'll use natural log of 2 over the half-life, which is 14.3 days. Approximately natural log of 2 is 0.693, divide by the half-life, which is 14.3 days, we find 0.0485. So to find the remaining fraction after 30 days, we'll use n over n naught, which is equals to exponential negative lambda t. So t is 30 days, and the decay constant, which is lambda, is 0.0485. So n over n naught is equals to exponential negative 0.0485 times 30 days, which will get negative 1.45401. If we apply exponential on this, we get an approximately 0.2336. So the remaining fraction is about 23% of phosphorus P32 atoms that remain after 30 days.
I am Moses Kiroi, registration number EDS 1034/15. I'm here to handle the question number 3. That is to calculate, using an example, to calculate the activity after 20 days. I'll start with the A, that's activity. A, 0 exponentials negative lambda t. That is, A is the rate of decay, and follow the same exponential law as the number of nuclei. Example, a sample of iodine 131, in bracket, T half is equals to 8 days. As an initial activity, A in bracket 0 of 400 mg grams. Finding decay constant in bracket constant is equals to 0.693 divided by 2, giving us 0.086 per day. You come and use the activity A at T is equals to 20 days, using A is equals to A0 lambda T. A is equals to multiply exponential in bracket 0.0866 multiplied by 20. That is 400. You multiply by exponential negative 1.732. That is 400 multiplied by 1.7693, giving us 70.7720 mg grams.
My name is Brian Korir, registration number EDN 3528/23, and I'm going to handle on question 4, which says explain the difference between activity and half-life. And we are going to see it on 4 cases, whereby we shall look at definitions, dependence, and units. To begin, activity is the rate at which radioactive decay occurs at a specific moment, of which it tells us how many atoms are disintegrating per second, while half-life is a time required for half of the radioactive nuclei to decay. So we can find that activity is about how fast now, while half-life is about how long it takes. Dependence. Activity depends on number of undecayed nuclei, n, whereby as n decreases, activity also decreases. While half-life does not depend on amount of substance. Whether it's small or large sample, the half-life remains the same. Okay, on units, activity is measured using becquerel, BQ, decay per second, while half-life is measured using units of time, that is seconds, years, and minutes. And that is the end of my discussion.
My name is Esther Chidosho. BSE 2654/23 is my registration number, and I'm going to explain 3 applications of dating techniques amongst many. So the first application is that it establishes chronological frameworks in archaeology and anthropology. For instance, we have the radiocarbon dating,
which estimates the age of organic materials like wood, bones, shells, which have up to over 50,000 years. We also have the potassium argon dating, which is used to determine the age of rocks and minerals by measuring the ratio of radioactive potassium. And finally, we also have another application, which is cultural heritage management, whereby it is used to authenticate the ceramics and paintings by determining their age and helping to identify forgeries.
So as we conclude, we've handled question 1, which was a calculation on half-life. We've calculated half-life of phosphorus after 30 days. We have known the differences between activity and half-life. We've also calculated example to calculate activity after 20 days, and we've handled applications of dating techniques. Thank you, Mr.